Hi everybody, welcome to the next lecture on computer animation. Today about interpolation and B-Splines. So here this curve shows an example of interpolation. So given are the points which are marked by the crosses here, which we call our control points. And then this dashed line here is an interpolated curve, which we would like to have to create nicely curved surfaces and curves. Yeah, so our general formulation again here as a repetition is that we have these three matrices and vectors to generate our curve in a parametric form. Right? So we had this vector which contains our helper variable u in different exponents up to 3 for cubic interpolation. Then we have our basis matrix, right? So those two together give us a set of polynomials. And here we have our control points, which define where in space our curve is lying and what shape it has. Right, so here we have 4 curves. So this is the general form which we used also for the Hermite and the Bézier curves. And then observe that the resulting points here are usually in 3 dimensions, so x, y, and z. Yeah, so that means that for each dimension we have the same type of interpolation with those polynomials. So for each dimension, okay. So this interpolation is a weighted average using our polynomials b1 up to b4. And remember, the sum was always 1 to get a convex hull, to get a curve inside the convex hull. So for each u we get a different weighted average value of the control points. So somewhere in this convex hull lies our interpolated point. Yeah, so in a way this is similar to the Nyquist sampling theorem. This is also a reconstruction of between sample values, right? So this reconstruction uses some sort of interpolation between our sample values. Right? Nyquist tells us we can take a low-pass filtered curve, so it's slowly changing, and then if we take this low-pass filtered curve and sample it, then if we sample it often enough, like more than twice the maximum rate of change of our curve, then we can perfectly reconstruct it. And it also tells us how we have to do it. It tells us that we can do this interpolation with an ideal low-pass filter. Right? And this ideal low-pass filter that should have a cutoff frequency which is equal to half the sample frequency. So the samples are now our control points here, and that means we need to adapt our low-pass filter to the sampling frequency, so how often those samples appear. We will see how that looks like graphically in a moment. The result of the low-pass filtering is then our interpolated curve. And the ideal low-pass filter's impulse response is a Sinc function. So that's what we know from Nyquist theorem. We have our ideal filter, which is a rectangle in frequency, so it passes the low frequencies, which means we have the transfer function equal to 1. And then in the stop band, we have the transfer function equal to 0, and that means we have basically a rectangular function in the frequency domain. And if we apply the inverse Fourier transform to obtain our impulse response, then this rectangular function becomes a Sinc function. Yeah, so this is again this interpolation. So here we have our samples or control points, and then here this dashed line is the interpolation which we might get from low pass filtering. So a Nyquist theorem makes sure that above the Nyquist frequency we have no frequency components present or no signal components. So maybe I should call this signal components. Right. So that means we have a minimum frequency of change and we have a maximum smooth curve. This interpolated curve here, the dashed line, is maximally smooth, which means it doesn't jump in between those control points, which is exactly what we want, right? We want to have a smooth interpolation here. Yeah, so this is the Sinc function that we need to use. So sine of pi t divided by pi t. And then low-pass filtering means a convolution of our sample points or control points with this function. Right. So here we can see it. So here we can see the Sinc function plotted. And we can see the integer values here. They are the positions of our samples or the control points. So here at each integer value, -1, 0, 1, 2, 3, we have a control point. So here those red circles are our control points, and then there's another one here at the top. And we can see that this curve here, the Sinc function, goes through zero at the integer points here. And that's an important character of this function, because that also means if we have one control point here and there are other control points here which might be not zero, and we add all those things up, that means that this function here from this control point does not influence anything at this position here. Right, so we will see how that works soon. Yeah, so that means samples and the other integer points are not affected by this point here in the middle. So that means the interpolation goes through the sample or the control points. Yeah, so we do this filtering with a low pass, and this is a convolution with a Sinc function. And we can rewrite our control points as a sequence of Dirac pulses for this convolution, right? We need to have some function which we convolve with. And the first function is a Sinc function that we just saw, a continuous function. But our control points, they are discrete. They are not really a continuous function. And that's why we need to translate it basically to a continuous space. And we do that using the sequence of Dirac pulses. Right, so basically at the position of each control point we have a peak, and this peak is our Dirac pulse, and in between we have zeros. Right? And in this way we have a correspondence from the discrete sample space to the continuous space for the interpolation. So here we can see the first function here might be our sequence of control points using the Dirac pulses. So here we have the shifted Dirac pulses and the position of each control point n. And here we have the value of the sample. X of n is the value of our sample of our control point here. Right, so here we have our sequence of samples in the first rectangular brackets, and then we convolve this now continuous function with a Sinc function which is also continuous, and we do that using here the convolution integral. So here you can see the convolution is defined as this integral, and this is the typical formulation. We can see one variable goes up in one of the function and the other one goes down. So here we can see we have this integral over n, and then it goes opposite directions. Yeah. Right. So here n usually is I use for integer values, but here we have this mapping from integers to continuous time, and that's why I can use it here in the form of a continuous variable. Yeah, so here this delta is the Dirac impulse or Kronecker delta, and the integral over this delta is defined to be 1. So we have an infinitely narrow peak and it's infinitely high, but it's defined as having an area of 1. So you can think of it as a triangle where the area is 1, and then you make the baseline of this triangle infinitely small, and then the top becomes infinitely high. Yeah, so then to simplify this expression, so here with this convolution expression that we just saw, here we have the sum of x times the shifted Diracs, and then we convolve it with a Sinc. Then we can take a look at this first part here, or the second part. Dirac convolved with Sinc. Right, here we can see it. We have a shifted Dirac convolved with our Sinc function, and the result is just the shifted Sinc function. Right, so this comes out of this convolution. So that's a very convenient result. So basically we get rid of this convolution in this way. So here originally the Sinc was centered around 0, and after convolution the Sinc will be centered around n. So then we can use that for our formula here. Basically we plug it into our sum. So then this sum turns into this simplified sum, and we can see that we have sampling points or control points multiplied by the correspondingly shifted Sinc function. So you can say that each control point or Sinc function, each control point or sample has its own Sinc function centered at its position. So each sample has a correspondingly shifted Sinc function multiplied with the value of the sample or the control point at that position. So and that can be seen here in this picture, in this example. So for instance here this red dot is one of the samples or the control points here at position 1. And then we have this red line, which is the correspondingly shifted Sinc function multiplied with the value of this sample, and that's why it's going right through this sample here. Same here with t equals 0. So here we have the first sample or control point, and we have this blue Sinc going through it. Right. So this is a non-shifted Sinc. It's at its original position multiplied with the value of the sample here. Then the red one is a Sinc shifted by 1 multiplied by the value of the sample. Then here the green line is the Sinc shifted by 2 multiplied by this value, and so on. Then we have another sample point here and the last one here. And each has its own Sinc function in a different color. And if we add up all those different Sinc functions, then we obtain this blue line. Right? And you can see this blue line indeed goes exactly through our control points or sample points in a very smooth way. Right? It has no kinks, very smooth, extremely smooth. And that's the advantage of this type of interpolation with using our Sinc function. It's really smooth. Yeah, so each control point has its own Sinc function touching it in its peak in the different colors. And the sum of these Sinc functions of our control points is the interpolated curve in black. Right. So we can also take a look at the Sinc function. It's sine divided by sine of x divided by x, or sine of pi x divided by pi x. And this sine function is an infinite polynomial, and hence also the sinc function is also an infinite polynomial, which means it is infinitely often continuously differentiable. And that also means that the interpolated curve is infinitely often differentiable. So that's great, right? So that's even better than, for instance, cubic splines, which we will see in a moment, which can only be continuously differentiated up to the second derivative, right? C2 continuity. Yeah, but can this approach be applied to the multidimensional? Well, actually, yes, it's easy because we can apply this interpolation separately to each dimension. As we can see here. So we have 4 control points. We define a sequence, like going this way, and in this way we can apply Nyquist interpolation to each dimension separately, and we can apply it to computer graphics. Yeah, so great so far, but the problem is the sinc function is infinitely long, which makes it unpractical, right? It's too complex to compute with many control points. That's why we are looking for alternatives, and a very, very simple alternative is the convolution of our samples instead of the infinitely long sinc function with the extremely short so-called box function as a basis function, which you can see here. So here's the x-axis, and this is just constant 1 in the first interval between 0 and 1, and then it's 0 for the rest. And if you have your samples on the integers, then you get something like a sample and hold function. So it takes the sample and holds it until the next sample arrives, and then it keeps that sample. But you can see here the function itself is then not continuous, it has jumps. Right? So we have interpolation, but it's not even continuous in the function value itself. So that's not so good. So we obtain the jumps. Here's a way to obtain C0 continuity. So the function itself is continuous, and this is basically the linear interpolation. Right? If we take the box function and convolve it with itself, then we get this triangular function. Right? And you can see here, this covers 2 unit intervals here, from 0 to 1 and from 1 to 2. So it's twice as long as the box function, and that's because of the convolution. And we have this triangular, which means we get 2 polynomials in 2 unit intervals. So this would be the first polynomial from 0 to 1. So this would be the polynomial u, if this axis is u. And this would be the polynomial 1 minus u. So this goes down if u goes up. Right, so we have 2 polynomials. And yeah, 1 minus u if we assume that u starts at 0 in this next interval. So u would be the local variable, goes from 0 to 1, and again goes from 0 to 1 here in the next interval. So that we have defined values of u for each of those polynomials. Yeah, so if we take this triangular function and convolve it with our sequence of samples as we did before, then we get these curves. So here is a triangular, the red one, then the blue one is the next triangular for the next sample, and so on. And if we add up all those lines, we get this dashed line, and this is a linear interpolation. Right? You can see here this sample only has contributions from its own triangle, but the other triangles are all 0. So the line goes through the samples. Yeah, so this gives us the linear interpolation. So C0 continuity. Yeah, so here we just saw the interpolated curve goes directly through our samples, and we get the C0 continuity, but we still have no C1 or C2 continuity for the first and second derivative. Right, so we have kinks in it. So the next step to obtain the C1 and C2 continuity is to do the same trick again. We convolve the basis function with itself. Right? And remember, convolution in time or space is multiplication in the frequency domain. So if you view our basis function, like here this rectangular, as a low-pass filter, right? So it's actually a very simple low-pass filter, as the Sinc function was a very sophisticated low-pass filter. Then when you look at this shape here we have the triangular in the rectangle in the time or space domain, and if you go to the frequency domain, it becomes a sinc function, and a sinc function is not a good filter, right, because of the ripples. And we want to make those ripples in the stop band as small as possible. And since those ripples are smaller than 1, we actually get some progress if we just square the sinc function. So we multiply it with itself. And multiplying the sinc function with itself means we convolve the function in the space or time domain with itself, which basically we did here, right? So this convolution in time or space leads to squaring of the sinc function, and that means lower ripples in the stop band and better attenuation, which means better low pass filter. So this triangle is already a better low pass filter. So now we can do the same trick again. We can square the squared sinc in the frequency domain. Then we have sinc to the 4th power, which means the side lobes in the stop band become even smaller. And that means we have this convolution again. So here we take two triangles, convolve them with itself, and since each triangle was itself a convolution of two box functions, we now have a convolution of 4 box functions. And this actually already yields our cubic B-spline. So it's actually quite a simple derivation of cubic B-splines. And this now covers 4 unit intervals, again because of the convolution, twice as much as the triangular. So the triangular had 2 unit intervals, convolution of 2 triangles gives us twice as many, and that's 4 unit intervals. So it becomes longer. And this is how it looks like. So here we have our 4 unit intervals, right? And here we get this shape. So it's now looking like a bell, a little bit like a bell-shaped curve. And since we have 4 unit intervals, that means we have now 4 polynomials, Q1, Q2, Q3, and Q4. And if you want to have C1 and C2 continuity, we have to make sure that the first derivative and the second derivative at the boundaries is continuous. So here at each boundary, all the derivatives and the function value itself need to be continuous. And for the construction of our B-splines, we have to take care of those conditions across those boundaries. Yeah, so how do we actually obtain this function here? Actually, I found that maybe the easiest way is to take the 4th derivative and then do 4 times integral. Because the 4th derivative is really simple, right? So actually we will see why this is. So we take the derivative rule for convolutions. Remember, B-spline was for convolutions. And if you take a derivative of a convolution of 2 functions, then it's the same as taking the derivative of one of those functions and convolve it with the other one. So you can actually distribute the derivative over the convolution. And here you can see why this is. Here you have the convolution integral, and if you take the derivative with respect to t, this t appears only in one of the 2 functions here, and you can draw it inside this convolution integral, and that means you have a convolution with a derivative of one of the functions. Yeah, so since we have 4 functions which we convolve, we can take the 4th derivative and distribute the derivatives over the 4 functions. Then we have a convolution of the derivative of 4 box functions. And the derivative of the box function consists of 2 Diracs. Right? Box function has an infinite slope at the beginning and the end. So it's increasing in the beginning and decreasing in the end. And that's why we have positive sign here for the beginning and negative sign here at the end of the box function. And if we take this expression and plug it in here in the convolution, and again, remember the shift rule, a function convolved with a shifted Dirac is a shifted function. So if we have 2 shifted Diracs and convolve them, then the shifts add up. And then you get this. So here you have the different total shifts, and here the factors come from the number of Diracs that have the same shift. Right? So this is then the result. So that means we can now integrate it once to get the third derivative. And the third derivative becomes piecewise constant because each time the integral passes 1 Dirac, its area is 1, so you just get the factor in front of it. So here the first Dirac was factor 1. So here factor 1, next one was factor minus 4. So here you can see it, first interval you get a 1, so here you can see a constant 1, until you get the next Dirac with minus 4, so you have 1 minus 4 is minus 3, then it stays constant until you get the next Dirac. The next Dirac had a factor plus 6, so that's why you end up at 3. Then you have another one with minus 4, and then you have another one with plus 1, and then you end up at 0 again. So this curve is now the third derivative. For the third derivative we have no continuity constraints, so we are fine at this point. So this is our third derivative. For the second and first derivative and the value itself, now we need to take care of the continuity. Right, so here we take a look at the first interval for u between 0 and 1, q1. Right, so here the third derivative of q1 in the first interval was 1, so here this 1. And yeah, so that's fine. So then we can take the second derivative by doing another integration. So here we get u, this polynomial u, as the second derivative. Another integration gives us the first derivative, u squared over 2. And another integral gives us the function itself, u squared over 6. So since we just have the first interval, for now we don't need to take care of any continuity constraints. We need to do that starting with the next interval. So here we have all the derivatives and the function value itself. And here you can see if we plug in 1 for u, then we get the value of this function at the end of this first interval where it touches the next interval. So the function value here is 1/6. Right. Yeah, and this is important for the next function value, or polynomial in the second interval. So here this is now about q2 of u. So we now know that the fourth derivative is minus 4 delta, and the third derivative was minus 3. So going back here, the third derivative in the next interval was minus 3. Right, this is the value here, and that means we can now compute the second derivative by integrating the third derivative, and we get minus 3u plus some constant c2. And this c2 now we need to choose such that the value of the second derivative at the lower end of the second interval is equal to the second derivative of the first interval at its upper end. So you can see it. Here the second derivative at the upper end, u equals 1. And when we go back here, the second interval had the polynomial u. So the upper end, u equals 1, means it has the value 1. right? So that's fine. So here, this has to have the same value for u equals 0, right? Because this is the lower end of the second interval. So that means C2 needs to be equals 1. So this is what we have here. So we need this for C2 continuity. So now we can plug this in, and we have the second derivative, minus 3u plus 1. Right. And now we can integrate it once more to obtain the first derivative, minus 3 over 2 u squared plus u plus another constant u1. Oops. Where did it go? Yeah, so here go. So plus c1. So now you can also plug and take the first interval, first derivative of the first interval, plug in the upper end for u equals 1. Right, so going back here, u equals 1 means you get 1/2. So here 1/2, and that means C1 needs to be 1/2 if we set u equals to 0 for the second interval. Yeah, and that means we can now plug it in. So this is then our polynomial for the second derivative. Now we can integrate it again. We get a constant C0 now. And now we need to make sure that the function value itself of this second interval at the lower end and of the first interval at the upper end are the same. So we saw that the so we saw that the first interval at value 1 is 1/6, and yeah, this should be 1 here, and that means C0 is 1/6. Right, so that means we can now plug it in here, and we get the polynomial for C0 continuity for the second interval. And we can factor out 1/6, and this is the polynomial that we get. Yeah. So we can now also plug in u equals 1 for the upper end of the second interval, and this is what we get. And remember, the upper end of the second interval was the center of our bell-shaped curve, and we see it's 4/6, and we also see it's less than 1. And that means it doesn't go through our sampler point. It just goes along. Yeah, and basically we could do the same for the last two intervals, but since we know we have a symmetric shape, we can take advantage of it and just mirror the polynomials, the first two polynomials, by replacing the hypervariable u by 1 minus u. So this basically means we go backwards and mirror it in this way. So here we take Q3, which we obtain by mirroring Q2 by replacing u by 1 minus u. And I do it using the software Maxima, which is an open source software for symbolic computations like this. And this is then the resulting polynomial. Similar for the last polynomial, which I obtain by mirroring the first one. This is the final polynomial. Yeah, so all together we have those 4 polynomials now. Right. And here we can see we have polynomials and coefficients, and this fits into our basis matrix. So here we have our exponents of u, of our helper variable u again, and we just plug in the coefficients here for each polynomial, for each basis polynomial. So here b4, b3, b2, and b1 times 1/6. Yeah, and since we saw it's not going through the control points, since the maximum value is not 1, and it's also not 0 at the other integer points, that means we get something like this. Here the crosses are again our control points, and then the blue line here shows a interpolation which goes along those points, but not exactly through them. In reality, it would be inside, because the sum is always 1, so it's inside the convex hull. Yeah, so the interpolation that we now have no longer goes through, but along the control points. So H4, our B-spline is not 0 at the other control points. This has to be considered during design, right? We need to maybe shift the control points accordingly. Yeah, so the advantage of cubic B-splines is that we have fixed basis functions, right? We saw we have this fixed basis matrix, which we can now store in our computer, and then it's done, right? We can use it for all the control points. And that's different from general splines, for which we actually have to compute those coefficients for each set of samples or control points. But the interpolated curve no longer goes through the control points, but they are within the convex envelope, or let's call it hull, convex hull. Right. Yeah, and cubic splines, they go through the control points, but the basis functions are not independent from the control points, which means we get higher computational complexity, and the curve is not within the convex hull. And that's why they are not used, right? Those are two very good reasons for not using them in computer animation or computer graphics. Yeah, so here's a practical verification of our theoretical derivation in Octave or MATLAB. So here basically I'm constructing my, my box function. So here basically I approximate this box function, which is defined in continuous time using discrete time, meaning 10 sample points. So 10 times the 1. Right, so the dx basically, or delta x here is 0.1, it's 0.1, so that's our spacing here. So dx equals 0.1. So that's why for H2 we convolve it with itself, and then we have this dx here times 0.1 for the integral, right? So here this convolution times this dx is approximating our integral. Same for H4, right? And then we can plot those four functions, and we can also compute the derivatives or approximate them by just convolving each function with a 1 minus 1. So these are the differences of two neighboring points, and this is then the division by dx, right? So this is an approximated differentiation. So here we have first derivative, second, third, and fourth. Let's see what we get. So here is our bell-shaped function, the H4, which are obtained by the convolution of four box functions. So that looks good. This is the first derivative. This is the second derivative, still continuous. Here we have the third derivative. This now has jumps, as we can see here. So this is the computed curve that we also got. Remember that now 10 is the unit interval, the first 10 is the first unit interval, the next 10 is the second, and so on. And this is now the fourth derivative. And you can see here we have those triangles. Those triangles approximate now the Dirac pulses. The area is still 1. So here you have well, the area should be 1 if you multiply it with a dx. Right, so we have here you have minus 40, and if you multiply it with a dx, you have minus 4. So that works. We get this factor here. Yeah, this is the reference, wavelets and filter banks, which also describe the B-splines. And here is now a Python example for using the B-spline interpolation in Opencv. So here we use the script for the Bézier curves and simply replace the Bézier polynomials with the B-spline polynomials. So let me open them. So I open a terminal window and open it in an editor. B-spline, interp.py. Yeah, so here you can see the content is basically the same as for the previous parametric curves, the Hermite and Bézier. Here, display function, virtual camera is defined, colors are defined, and here the points are now defined. So here we have our 4 control points, P0 to P3. And here I'm making the points of those control points. I'm plotting them in our virtual world. And here I'm doing the interpolation. So again, I'm having 10 points for our helper variable u between 0.1 and 0.9. And here I have 4 polynomials, which are now the B-Spline basis polynomials. Right? So before we had Hermite or Bézier polynomials here. Now we just replace them by our B-Spline polynomials. So software on the software side is basically almost the same as the previous parametric curves, just with different polynomials. So here we can print the values for each u, and here the sum for each u. So the sum should again be 1. And then we plot those interpolated curves here. So let's see how it looks like using Python 3. Yeah, so here you can now see it. So the red dots are the control points again. And now you can see we have a relatively narrow curve here. This is what's quite different from Bézier or Hermite, right? For Bézier, we had a curve which started in the first and ended in the last point and went along the 2 middle points. Now we have a much shorter curve. It's not starting and ending somewhere, it's just starting and ending in the middle somewhere. It's inside the convex hull, so that's already obvious. And it only has this very small curve here, basically. So this already looks like it waits for continuation by another point, right? So let's take a look at the values of the polynomials, which we can see here. And we can see it always adds up to 1. So that confirms that the points are inside the convex hull. Yeah, so that works. It's nice smooth, but just a little short. Right, so let's go to the next one. So here you can see that we can add another interval by adding a 5th point, right? So now basically we get 2 interpolated lines, one for the first 4 points, and then the next interpolated curve for the next 4 points, and there's an overlap of 3 points between them. Right? So the new interval is created by interpolating the last 4 points. Only the first point of the previous interval is missing. Right? So we can take a look at it. So let me also open it here in gedit. So 2 intervals. Oh, that was not the editor. So let me open the editor, gedit. Yeah, so here you can see it, the points, and now I added this 4th point here. Right, and here it's plotted. Or rather the 5th point, so 0 to 3 are the first 4 points, and this is the 5th point. And now we basically get 2 curves. So again, here we have our interpolation using u between 0.1 and 0.9 in 10 steps. Here I'm computing the values of my polynomials. I'm printing the values and the sum again. But now I have 2 interpolated values. Once here for the first 4 points, P0 up to P3, and then here for the second interval. but now for the points P1 to P4. So you can see P1 to P3 appears in both intervals, but the first interval has P0 and the next one has P4. So this way we get two different interpolated curves on the same plot. And now let's take a look how it looks like if they nicely mingle and mix. Python 3. Yeah, so here you can see the result. So here's the first interpolated curve, and the next one immediately follows the first one. So actually they nicely mix and mingle in the way that basically they touch each other here at this point here in the middle. And then they continue in such a way that it's very smooth. Right? So actually this way here we have the C0, C1 and C2 continuity at this point here. This is what we just made sure by constructing our polynomials accordingly. Right? To have that we have a very smooth continuation of the curve here. Maybe you can also take a look at it by increasing the range here. So we go from 0 to 1.0 and maybe take 100 points. Then the smoothness should become much clearer. Yeah, so you can see it. So you can't even see where those two curves touch because it's one smooth curve. Right, so that works nicely. And it works nicely because we gave the polynomials this property. Right, so let me go back here to the original values. Yeah, so that shows it works indeed. Yeah, so the curves of the two intervals are in fact smooth overall. And in this way we can always attach more points to it and obtain an increasingly long smooth C2 continuous curve. This is the new feature in comparison, for instance, to the Bézier curves. So here actually we can just add more and more points and don't worry about the connection because those polynomials take care of the connection for us. Right, so that's very practical. Plus, it's not more computation complex than Hermite or Bézier, and unlike the Sinc function, which is extremely complex. So that's fine. Yeah, now we can compare it with a general cubic spline curve. So here I made an example for it. So let me open gedit spline. So you can do it if you want, but so here again you have those 5 points here, and here you have the spline interpolation. So here I have an x and a y. Right, so you need this, and this is the basically the x coordinate, and this is the y coordinate, and you need to now specify those coordinates because you first need to compute a cubic spline according to those coordinates such that it goes right through those coordinates. And this shows you the problem with those generic splines. The coefficients of your splines depend on the coordinates. Right. Here I'm computing the coefficients explicitly using this function here. And yeah, so interp is, let's see, it's actually part of SciPy interpolate that gives us this object interp, or this library interp. Here SciPy interpolate, and has many interpolation functions, and I'm using it here to construct cubic splines. So here the kind is cubic. Here is the helper function u, and x is and x and y are the coordinates that we want to approximate. And you can also see that we need different polynomials for each coordinate. Yeah, so then I can do the interpolation in the same way. Here I'm using lin space between 0.1 and here 3.9. So that works for the entire range, not just the unit interval, using the 30 points. So basically the same density. And here I'm then plotting those 30 interpolated points. So let me try that. So Python 3. Yeah, also observe that it needed to have that this polynomial needed to go through all those points. So if I had another one being added here, it would not necessarily be continuous for the first or second derivative. So that's another disadvantage. Yeah, you can see it's going smoothly through those control points. That's good. But it's also not inside the convex hull. So when you look at the convex hull here, see this arch here is outside the convex hull. So that's another disadvantage. So that's all why this is not used for computer animation or computer graphics. It's too complex, it's not inside the convex hull. Also the continuity is not really guaranteed across those intervals. So it's not so practical for computer graphics. Yeah, and that should be it for this set of slides. So next time we will talk about rough interpolation. So thanks for your attention and see you in the next video.